the sum of the first, second, third, and fourth terms 1 plus 2 plus 4 plus 8 equals the fifth term 16 minus 1. In a series of evenly even numbers, the first multiplied by the last equals the last, the second multiplied by the second from the last equals the last, and so on until in an odd series one number remains, which multiplied by itself equals the last number of the series. Or, in an even series two numbers remain, which multiplied by each other give the last number of the series. For example 1, 2, 4, 8, 16 is an odd series. The first number 1 multiplied by the last number 16 equals the last number 16. The second number 2 multiplied by the second from the last number 8 equals the last number 16. Being in odd series, the 4 is left in the center, and this multiplied by itself also equals the last number 16. The evenly odd numbers are those which, when halved, are incapable of further division by halving. They are formed by taking the odd numbers in sequential order and multiplying them by 2. By this process the odd numbers 1, 3, 5, 7, 9, 11 produce the evenly odd numbers 2, 6, 10, 14, 18, 22. Thus, every fourth number is evenly odd. Each of the even-odd numbers may be divided once, as 2, which becomes 2 ones and cannot be divided further. Or 6, which becomes 2 threes and cannot be divided further. Another peculiarity of the evenly odd numbers is that if the divisor be odd the quotient is always even, and if the divisor be even the quotient is always odd. For example, if 18 be divided by 2 an even divisor the quotient is 9 an odd number. If 18 be divided by 3 an odd divisor the quotient is 6 an even number. The evenly odd numbers are also remarkable in that each term is 1/2 of the sum of the terms on either side of it. For example, 10 is 1/2 of the sum of 6 and 14. 18 is 1/2 the sum of 14 and 22. And 6 is 1/2 the sum of 2 and 10. The oddly odd, or unevenly even, numbers are a compromise between the evenly even and the evenly odd numbers. Unlike the evenly even, they cannot be halved back to unity. And unlike the evenly odd, they are capable of more than one division by halving. The oddly odd numbers are formed by multiplying the evenly even numbers above 2 by the odd numbers above 1. The odd numbers above 1 are 3, 5, 7, 9, 11, and so forth. The evenly even numbers above 2 are 4, 8, 16, 32, 64, and soon. The first odd number of the series 3 multiplied by 4 the first evenly even number of the series gives 12, the first oddly odd number. By multiplying 5, 7, 9, 11, and so forth, by 4, oddly odd numbers are found. The other oddly odd numbers are produced by multiplying 3, 5, 7, 9, 11, and so forth, in turn, by the other evenly even numbers 8, 16, 32, 64, and so forth. An example of the halving of the oddly odd number is as follows: 1/2 of 12 equals 6. 1/2 of 6 equals 3, which cannot be halved further because the Pythagoreans did not divide unity. Even numbers are also divided into 3 other classes: superperfect, deficient, and perfect. Superperfect or superabundant numbers are such as have the sum of their fractional parts greater than themselves. For example, 1/2 of 24 equals 12. 1/4 equals 6. 1/3 equals 8. 1/6 equals 4. 1/12 equals 2. And 1/24 equals 1. The sum of these parts 12 plus 6 plus 8 plus 4 plus 2 plus 1 is 33, which is in excess of 24, the original number. Deficient numbers are such as have the sum of their fractional parts less than themselves. For example, 1/2 of 14 equals 7. 1/7 equals 2. And 1/14 equals 1. The sum of these parts 7 plus 2 plus 1 is 10, which is less than 14, the original number. Perfect numbers are such as have the sum of their fractional parts equal to themselves. For example, 1/2 of 28 equals 14. 1/4 equals 7. 1/7 equals 4. 1/14 equals 2. And 1/28 equals 1. The sum of these parts 14 plus 7 plus 4 plus 2 plus 1 is equal to 28. The perfect numbers are extremely rare. There is only one between 1 and 10, namely, 6. One between 10 and 100, namely, 28. One between 100 and 1000, namely, 496. And one between 1000 and 10,000, namely, 8128. The perfect numbers are found by the following rule. The first number of the evenly even series of numbers 1, 2, 4, 8, 16, 32, and so forth is added to the second number of the series, and if an incomposite number results it is multiplied by the last number of the series of evenly even numbers whose sum produced it. The product is the first perfect number. For example, the first and second evenly even numbers are 1 and 2. Their sum is 3, an incomposite number. If 3 be multiplied by 2, the last number of the series of evenly even numbers used to produce it, the product is 6, the first perfect number. If the addition of the evenly even numbers does not result in an incomposite number, the next evenly even number of the series must be added until an incomposite number results. The second perfect number is found in the following manner. The sum of the evenly even numbers 1, 2, and 4 is 7, an incomposite number. If 7 be multiplied by 4, the last of the series of evenly even numbers used to produce it, the product is 28, the second perfect number. This method of calculation may be continued to infinity. Perfect numbers when multiplied by 2 produce superabundant numbers, and when divided by 2 produce deficient numbers. The Pythagoreans evolved their philosophy from the science of numbers. The following quotation from Theoretic Arithmetic is an excellent example of this practice. Perfect numbers, therefore, are beautiful images of the virtues which are certain media between excess and defect, and are not summits, as by some of the ancients they were supposed to be. An evil indeed is opposed to evil, but both are opposed to one good. Good, however, is never opposed to good, but to two evils at one and the same time. Thus timidity is opposed to audacity, to both of which the want of true courage is common. But both timidity and audacity are opposed to fortitude. Craft also is opposed to fatuity, to both of which the want of intellect is common. And both these are opposed to prudence. Thus, too, profusion is opposed to avarice, to both of which illiberality is common. And both these are opposed to liberality. And in a similar manner in the other virtues. By all of which it is evident that perfect numbers have a great similitude to the virtues. But they also resemble the virtues on another account. For they are rarely found, as being few, and they are generated in a very constant order. On the contrary, an infinite multitude of superabundant and diminished numbers may be found, nor are they disposed in any orderly series, nor generated from any certain end. And hence they have a great similitude to the vices, which are numerous, inordinate, and indefinite. Insert. The sieve of Eratosthenes. Redrawn from Taylor's Theoretic Arithmetic. This sieve is a mathematical device originated by Eratosthenes about 230 BC for the purpose of segregating the composite and incomposite odd numbers. Its use is extremely simple after the theory has once been mastered. All the odd numbers are first arranged in their natural order as shown in the second panel from the bottom, designated odd numbers. It will then be seen that every third number beginning with 3 is divisible by 3, every fifth number beginning with 5 is divisible by 5, every seventh number beginning with 7 is divisible by 7, every ninth number beginning with 9 is divisible by 9, every 11th number beginning with 11 is divisible by 11, and so on to infinity. This system finally sifts out what the Pythagoreans called the incomposite numbers, or those having no divisor other than themselves in unity. These will be found in the lowest panel, designated primary and incomposite numbers. In his History of Mathematics, David Eugene Smith states that Eratosthenes was one of the greatest scholars of Alexandria and was called by his admirers the second Plato. Eratosthenes was educated at Athens, and is renowned not only for his sieve but for having computed, by a very ingenious method, the circumference and diameter of the earth. His estimate of the earth's diameter was only 50 miles less than the polar diameter accepted by modern scientists. This and other mathematical achievements of Eratosthenes, are indisputable evidence that in the 3rd century before Christ the Greeks not only knew the earth to be spherical in form but could